Kia ora and welcome back. In this video we're going to continue talking about viscous flow, and we're going to talk about a phenomenon called turbulence. So turbulence is essentially when a fluid is flowing. We know that if there's viscosity involved, the fluid doesn't all just flow together. The parts of the fluid are moving faster than others, which creates a kind of friction inside the fluid. And if this gets extreme enough, like for example if the fluid is flowing fast enough, then you lose this sort of nice smooth flow and it all breaks down and becomes turbulent and choppy. So we're just going to talk a little bit about that in this video and how we can tell if it's going to happen or not. So first off, we've got two different types of flow we're going to talk about. The first kind of flow is what we call laminar flow, and that's illustrated in this top picture here. When everything's flowing nicely together, if you maybe put a little particle into your fluid, it's just going to go along a nice streamline like this. It's not going to do anything weird, and everything is just nice and orderly and uniform, and everything is happy. So that's laminar flow. You get everything settles down and is constant. Nothing is changing over time once it's settled down. You get laminar flow when the fluid is flowing slowly. So for example, a nice flowing stream. I've got a picture here of a river in Banff, and you can see laminar flow approximately is this part of the stream where everything's sort of nice and quiet and flowing nicely. And the deeper it is, you'll see that it can look even smoother than this. This maybe is slightly windy on top. When there is turbulence, that is when you get that when you've got a higher flow speed. And everything gets irregular because you get these little vortices spinning around inside your fluid, and everything just looks like a choppy mess. So for example, if you just turn a tap on, you've probably noticed sometimes you get a nice smooth stream at the top of your flow, but as the water's falling, it accelerates, and by the bottom, it can all sort of break up and become kind of messy. That's also an illustration of this. And on a river, we can see it where we have rapids or waterfalls. So in rapids here, all that means is that the river is shallower, so the water has to flow faster to get through, and that's when it becomes turbulent. All right, so it turns out if we're looking at a pipe, there is a single number that we can calculate that will predict for us whether we'll have turbulent flow or laminar flow. So the equation is quite simple. Again, just making a little note of this one. And it calculates a number called the Reynolds number. Reynolds number is what we call a dimensionless number, which means it doesn't actually have any units. And if you're looking for a fun exercise, you could just check that all of the units of the various quantities in that equation do actually cancel themselves out. So what do we got? Well, let's just have a look at the pieces. We need to know the density. That's what rho is. D is the diameter of our pipe, because we are looking specifically at a flow in a pipe with this equation, much like we were before. So D is going to be our diameter. Rho is the density. A is our area, so that's going to be this area here. This is A. And eta is our viscosity, and then Q is our flow rate. So combine all these factors together and see what number you get, and essentially that number will tell you whether you've got turbulence or laminar flow. So it turns out if your number is larger than 3000, then you will be looking at a flow that is pretty much guaranteed to be turbulent. If your number is less than 2000, then your flow is going to be laminar. And if you're somewhere in between, then what you'll get is a flow where it sort of changes. It's going to be oscillating between laminar and turbulent over time, and it's not going to settle down into any one particular kind of behavior. But if you're outside of those limits, then you can predict what the flow profile will look like, whether it will be the nice smooth laminar flow or the choppy turbulent flow. So let's return to our example from the last video where we were injecting a drug through a syringe. So once again, here's the syringe. It was 5 centimeters long. It had a diameter of 1 millimeter. And we worked out a few things about it. We worked out the flow rate. No, we were given the flow rate, but we worked out the flow rate in our correct units. And we've got this other bit of information, which is the density. And so let's see if we can figure out the Reynolds number for this flow to predict whether it's going to be turbulent or not. So it's just literally a matter of taking the equation and plugging all of the pieces in. So our equation says that the Reynolds number is equal to rho d over A eta all times Q. So before we put everything in, let's just write down what everything is and make sure we've got everything in the right units. So our density given to us as 1050 kilograms per cubic meter, which is in the right units, so that's good. We're going to need the diameter, and it's going to need to be in meters, so it's going to be 0.001 meters, or 10 to the negative 3 if you prefer. The area, now the area is going to be the area of a circle, so it's going to be pi times the radius squared, which is pi times half the diameter squared, which equals, I'll just leave the pi alone because I know that my radius squared is going to be relatively nice. 10 to, so it's going to be 0.5 times 10 to the negative 3, and we're going to square that, which is 2.5 times 10 to the negative 7 square meters. What else do I need? My viscosity has been given to me, but we'll just write it down anyway. That is the correct unit, 8.9 times 10 to the negative 4 Pascal seconds. And my flow rate has also been, we worked it out last video, as 1.67 times 10 to the negative 7 cubic meters per second. So literally all we have to do is plug this into our formula and just see what it comes out to be. So that will equal 1050 times diameter, which is 10 to the negative 3, divided by pi times 2.5 times 10 to the negative 7, times our viscosity, 8.9 times 10 to the negative 4, and it's all times the overall flow rate Q, which may as well be on the top of the fraction. It means the same thing, 1.67 times 10 to the negative 7. Again, we've got to be a little bit careful entering this in the calculator, especially make sure that you've put a bracket around the bottom of this calculation. Also, by the way, in case you didn't realize, your calculator probably has a shorthand for these powers of 10 notations. On my calculator, there's a button called EXP right in the bottom row, and that lets me enter a power of 10. So for the flow rate of, for the 0.5 times 10 to the negative, the 1050 times 10 to the negative 3 at the start, I can just go 1050 EXP for 10 to the negative 10, and then negative 3, and that will be that value. Okay, so let's type this all in. So I'm going to go 1050 EXP negative 3 times 1.67 EXP negative 7 divided by, open a bracket, pi times 2.5 EXP negative 7 times 8.9 times 10 to the negative 4, close my bracket, I've finished dividing now, and that tells me the Reynolds number is approximately 251, which is nice. So that's cool. So what's going to happen to our flow? Well, our flow will be laminar because it's less than 2000. Okay, so second part of the question. If our flow is increased to 250 milliliters per minute. Now remember, maybe we've forgotten, but the original question told us that the flow rate was 10 milliliters per minute. So what we've basically done here is we've increased our flow rate by a factor of 25 to up to 250 milliliters per minute. So now the question is, will the flow be laminar or turbulent? So an increase in flow rate means it's going to be moving faster. So the question is it enough faster to make us turbulent? Well, let's have a look. What I basically said here was my flow increases by a factor of 25. So essentially we're taking this Q here and we're replacing it with a new one, which is 25 times bigger. And you can see that the effect this will have on the equation is to multiply the Reynolds number by 25 as well. So what we'd say is Reynolds number is proportional to Q, so is 25 times bigger also, which means our Reynolds number will be approximately 25 times 251, which gives me about 6,270. Remember, there's no units, so it's just the number. And this is greater than 3,000, so flow is turbulent, as the Reynolds number is greater than 3,000. Okay, so what this tells us is essentially that if we increase the speed of our flow, or the flow rate, then our flow has transitioned from being laminar to turbulent. So whenever we have flow in a pipe, we can just work out the Reynolds number using our Reynolds number equation and tell what kind of flow we're going to have. And sometimes turbulence can be a good thing. For example, if you've got something dissolved in your liquid, or you're trying to have something dissolved in your liquid, then making the flow be turbulent will agitate it a whole lot and maybe make it easier to dissolve something and mix it through. So sometimes turbulence can be a desirable property of fluid flow. It's not always a bad thing, but often if we just want sort of efficiency, then laminar might be what we're after. Anyway, we'll call that a day there, and we'll see you next time. Ka kite anō.